Okay, so this will actually be, and you might go ahead and mark it, this will be for section 4.6, and this is on related rates of change. On these problems, they're going to give you a rate at which something's changing, and they're going to ask for a rate at which something's changing. Okay? And so this is an example. I want to go through this. Okay? It says Borg the turtle was walking across the road to get to the other side, and a very weird person saw him. Mr. Turtle tried to get away, but alas, he was not so fast. The person subjected Borg to genetic engineering to grow fur on the turtle. Assume Borg is semi-spherical. Okay, I would highlight that. That's giving you a clue what formula. And the hair grows equally and only on the curved surface. Include hair in the radius and round answers to 3 decimal places. Okay, on the first part, when the rate of change of the volume is 12 cubic feet per second, and Borg has a radius of 14 feet, it's one huge turtle, what's the rate of change of the radius? Okay, now, they're giving us a rate of change of the volume, and they're asking for a rate of change of the radius. Okay, now, let's go through this together. Okay, so you need to put this on another sheet of paper. Okay, so first, and you probably would not have this memorized, so you may have to go out on your iPads and look up the volume of a sphere. Okay, because it said semi-spherical. So for a sphere, okay, the volume is 4/3 pi r cubed. But instead of it being a sphere, it's actually like the body is semi-spherical, something like that. So it's half of that. Okay, so semi-spherical okay, the volume is 1/2 times 4/3 pi r cubed. If we simplify that, we could reduce, and we end up with semi-spherical is 2/3 pi r cubed. Okay, so that's the formula we're going to use. Now, when you do this, you have to differentiate this on both sides with respect to time. So let's go ahead and put that outside. So a year from now, if you come back to this, does that look right? Differentiate. Differentiate both sides. WRT with respect to time. And that means we're going to use the chain rule. And the idea is to find an equation, use the chain rule to find an equation that relates the rate we know to the rate we want to know. To find an equation that relates the rate we know to the rate we want to know. And that's why it's called related rates of change problems. Okay? Okay, so the way you do this is you differentiate both sides. So on this line, if we differentiate this side, it would be the rate at which the volume is changing with respect to time. When you read that, the dV over dt, that's the rate at which the volume is changing with respect to time, equals. Now, when you do this, the variable is the r. So we're going to take this 3 times the 2/3. So that's just going to give us 2. The pi is a constant, so it's going to stay. You depress that exponent by 1, okay? And then it's kind of like the implicit differentiation. It's times the rate at which the rate is changing, or the radius is changing, with respect to time. You have that dr over dt, okay? So here's the rate we know, right? Didn't they give us that? And this is the rate we want to know. Okay, so now you solve it. Okay, so the rate we know was 12. And then 2 pi. The r, they gave us the radius was 14 squared. And we're trying to solve for the rate at which the radius is changing with respect to time. Okay? Okay, so we can divide on both sides. We can divide this out. Okay. You can simplify you can reduce the 2 and the, okay. Now take 6 divided by. Now, if you do this on the calculator, you make sure you put parentheses around, okay. Go ahead and divide that out. Use the pi key on your calculator. And go 3 decimal places. We round it to 3 decimal places. What do you get? Yep. And then if you 0.0097, right? And then that would be in feet per second. Now, if we round that to 3 decimal places, that means we've got to round this up. No, sorry. We got to go round this one up first, which makes we round the other one up. So it's 0.010. You agree with that? And that's the rate at which the radius is changing. So basically, these problems, 2 things are going to happen at the same time. If this one, they gave us the volume was changing at 12 cubic feet per second. So this turtle is growing. The volume's growing, but the radius is also growing at the same time. So it's growing at a rate of 1/100th of a foot per second. Okay? Okay, that's part 1. Okay, part 2. Okay, go back to the second. Okay, part 2. The weird person wanted Borg to be huggable soft. This occurs when the rate of change of the volume, okay, rate of change of the volume is 1,600 cubic feet per second. That's huge. And the rate of change of the radius is 13 cubic feet per second. When did Borg reach huggable soft status? Okay, basically give the radius. Okay, read that one more time. They're giving us the rate at which the volume's changing. What's the 13? The change of the radius. That's not the radius. We're solving for the radius. So basically they're giving us both rates of change. Okay, so let's go back. Okay, so for problem number 2, same formula, we've already worked it out. The rate at which the volume's changing with respect to time equals 2 pi r squared times the rate at which the radius is changing with respect to time. Okay, they told us the rate at which the volume is changing. Whoops, hang on. They told us the rate at which this is changing is 1,600. Okay. We don't know the radius. We're trying to solve that. They did tell us the rate at which the radius is changing is 13. Okay. Now, solve that for r. Okay. So go ahead and divide. So basically you're dividing by 26 pi on both sides. Okay. And you got to remember you're figuring r squared. All right. If you do this on the calculator, remember you want to divide that out, put parentheses around it. Did you get like 19.588 for r squared? Now take the square root of both sides, and then round your final answer. I got 4.426 if you round it. Okay, and that would be in feet. Okay, because we're solving for radius. It's not a rate, it's a radius. So 4.426 feet. Okay. Okay, so when you do these problems, the related rate problems, it's critical that you figure out what formula. Okay, if they don't give you the formula, you may have to look it up. Volume of a sphere, you know, if you didn't have that memorized, you got to go back and look it up. Okay, and it was semi-spherical, so we had to take half of it. Then you've got to differentiate on both sides with respect to time. Okay, and it's kind of like when we did the implicit differentiation, and we had the extra, every y term had that extra dy over dx. Remember that? So you're using the chain rule and kind of the implicit differentiation. Okay, and then from there you just substitute in. Okay. Okay.